In this session, I'll show a simple motor model. It's a simple way to model a motor where we can include leakage instead of using the volumetric efficiency. So including the leakage directly, such that it is pressure dependent. We will still not go into modeling the internal part of the pump or motor. So let's put up a sketch. Here we have our motor. And when we run it, it has some rotational velocity. And to include the leakage part, what I will do is to add this parallel path here and illustrate like this, that is not an orifice that I'm modeling, but a laminar orifice, you could say. But it's a laminar flow that I'm modeling in parallel with the motor. So now we define the pressure P1 and P2 before and after the motor. So let's now try and see what is the flow through the motor and what is the flow through this laminar system that we have here. So if we define a flow through the motor, and then we define a flow as our leakage flow, then the motor flow will be the displacement of the motor times the rotational velocity of the motor. Our leakage flow, we define that as a leakage coefficient multiplied with the pressure difference across the motor. So here you have the two flows that we model through our motor. So we should see all of this as something that happens inside the motor. So we have the connection out here and the connection out here. We might also have a drain port connected out here. So now, what is the torque that the motor will deliver out here? Well, the torque of the motor, we have the displacement where we remember to have it in the SI units. So it needs to be cubic meters per radian. And then we multiply that with the pressure difference. We can include some friction term, which is here said to be dependent on the motor velocity. If you wanted to model this system in a dynamic way, and when we needed to set up continuity equations for the pressure 1 and the pressure 2, then let's assume that we have a Q1 flow that comes in and a Q2 flow that goes out. This control volume that we have up here, 1, that is until we have something where we have a different pressure level, right? So it could be including the hose connection or the pipe connection to the motor. So if we set up continuity equation, the general continuity equation where we have flow in, flow out, change in volume, the volume over bulk modulus times our pressure gradient. So let's set that up for our two control volumes. So saying that we have a control volume 1, the flow in will be Q1 minus what is then the flow out. We have a leakage flow, we have a flow through the motor. Change in volume will be 0. Setting the same up for control volume 2. And here I have on purpose put the flow through the pump as a change in volume. Sometimes you'll see it modeled like this, other times you'll see it modeled like this. And if we look at what is it up here, then we see that we have a displacement times a rotational velocity. So it is some volume that we're moving from one point to another point. A bit like what we had for the cylinder. For the cylinder we had a times a velocity, the displacement flow. So this is what we have for the cylinder. And if we wanted to go more into what is these volume changes inside the motor, well, then it's another level of model that you should do. So for this model here, we could set it up like this. So now we have something that describes the pressure here and here. We have all the flow defined, and we have our torque that we deliver out to the system.